Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today's topic of discussion is synchronous generators. Our objective is to examine electrically excited synchronous generators on an introductory basis. We'll explore those mechanical and electrical properties that influence resultant electrical power output. This lecture is limited in scope to synchronous generators in unloaded, isolated conditions and does not discuss how generators react to different load conditions nor generator synchronization. We'll explore loaded synchronous generators and generator synchronization in greater detail in later lectures. This lecture operates under the presumption that viewers watch the electrically excited synchronous motors and synchronous condensers lectures, both available at the Big Bad Tech channel. Additionally, this lecture operates under the presumption that viewers have some level of familiarity with squirrel cage induction motors and asynchronous or induction generators. We'll use this prior understanding as a basis of comparison for today's discussion about electrically excited synchronous generators. If you haven't watched these lectures yet or only dimly recall their contents, please bring yourself up to speed and return when you are so qualified. In the aforementioned lectures on asynchronous or induction generators, we'll learn that asynchronous generators necessitate connection to a previously established three-phase AC system. As we learned, a portion of the power an asynchronous generator necessarily draws for operation is directed towards a reactive interchange and goes towards establishing the rotating magnetic field in the stator. This implies asynchronous generators continually consume reactive power, even when exporting real electrical power for use. In summary, it takes power to make power. Additionally, an external prime mover must turn an asynchronous generator rotor faster than the synchronous speed of the stator for induction to take place. Synchronous generators, the topic of today's discussion, in contrast, can operate without an external three-phase AC power source and are black start capable, meaning from utter darkness, i.e. a grid in a completely depowered state, they can begin generation even if in isolation. For this reason, a vast majority of large mission-critical generators like hydropower dams and coal-fired power plants are synchronous generators. Additionally, synchronous generators, given proper control mechanisms, can operate at unity power factor, i.e. neither supply nor consume reactive power. Finally, an external prime mover must turn the rotor of a synchronous generator at synchronous speed. Again, the primary distinctions between asynchronous or induction generators and synchronous generators, the topic of today's discussion, are as follows. Asynchronous generators necessitate connection to an existing three-phase AC power grid. Synchronous generators, in contrast, can exist in isolation and are black start capable. Asynchronous generators must continually consume reactive power to power the induction process central to their operation. Synchronous generators, in contrast, can operate at unity power factor given proper control mechanisms. And finally, the rotors of asynchronous generators must turn faster than the synchronous speed of the stator, whereas the rotors of synchronous generators must turn at synchronous speed. Lastly, to make one more subjective distinction between these styles of generators, I should also mention that induction-style generators have a general tendency to be large in number but small in size, principally because they are relatively inexpensive and simple to operate, whereas synchronous generators are few in number but large in size, principally because they are somewhat more costly and complicated to operate. There are obvious exceptions to these sweeping generalities. Let us briefly review the parts of a synchronous machine. As you are no doubt aware, an electrically excited synchronous machine consists of three electrically isolated windings in the stator in a Y or a delta configuration and a DC field winding on the rotor. The rotor field winding is accessible via a set of slip rings which maintain electrical connection regardless of rotational position to a stationary DC source known as an exciter. In motor mode, three-phase AC is supplied to the stator windings, which create a rotating magnetic field. The rotor is then energized by DC electricity, which establishes an electromagnet. The electromagnet on the rotor locks into the stator rotating magnetic field and follows it around and around and around. As long as the load torque remains under the pullout torque for that particular level of DC excitation in the rotor will maintain synchronous speed and stay locked in step with the rotating magnetic field on the stator. In summary, while in motor mode, the stator consumes AC electrical power. The rotor consumes DC electrical power. This incoming electrical power is converted into mechanical power in the form of rotational speed and torque. The other aspect of synchronous machines, generator mode, is slightly different. In generator mode, the rotor is energized by DC electricity, which establishes an electromagnet. Then some outside force known as a prime mover, either falling water, moving wind, expanding steam, or an internal combustion engine, turns the rotor inside the stator. As the electromagnet on the rotor passes in close proximity to the stator windings, a voltage is induced across the stator windings. In summary, while in generator mode, the mechanical power of the prime mover and the DC electrical power consumed by the rotor is converted into AC electrical power output on the stator. The simplification of the generation process implies a certain dependency between the mechanical and electrical properties and the physical construction of the synchronous generator and the resultant AC electrical power output. The goal in today's lecture is to determine which input properties influence which outputs and demonstrate how one goes about establishing electrical output with the specified parameters. Of primary concern regarding the desired electrical output are four important properties: phase sequence, phase shift, frequency, and voltage magnitude. Let's deal with phase sequence first, since it's probably the most intuitive of these properties. Rotational direction of the prime mover influences which winding experiences peak voltage in relation to its peers. Using this simplified diagram, when rotated in a counterclockwise direction, first winding 1 experiences peak voltage, then 2, then 3. In contrast, when rotated in a clockwise direction, first winding 3 experiences peak voltage, then 2, then 1. In summary, rotational direction of the prime mover determines phase sequence. Phase shift, in contrast, has to do with the number and the physical placement of the windings on the stator. Using this simplified diagram with 3 windings, each with a relative 120-degree physical offset, each winding experiences peak voltage at a relative 120-degree electrical offset. This is a common arrangement for industrial 3-phase AC throughout the world, albeit not the only means of making multi-phase AC. For example, consider a 4-phase AC system with 4 windings at 90-degree offsets, or a 5-phase AC system with 72-degree offsets, and so on. In summary, the physical construction of the stator windings influences the degree of phase shift between the related phases. Let's now take a look at frequency and voltage magnitude. Frequency would measure how many cycles of voltage waveform it experiences per second, measured in units of hertz, where 1 hertz is 1 cycle per second. A related property, period, is the length of a single cycle. Period is the inverse of frequency, and frequency is the inverse of period. It stands to conjecture that the faster the rotor electromagnet turns inside the stator, the more frequently each stator winding experiences a full cycle of voltage, thus resulting in higher frequency output. In contrast, the slower the prime mover drives the rotor electromagnet inside the stator, the less frequently each stator winding experiences a full cycle of voltage, thus resulting in lower frequency output. Long story short, the rotational speed of the prime mover directly influences output frequency. Thus far, we've discussed phase sequence, phase shift, and frequency. So we're left with one electrical property, voltage magnitude. What controls voltage magnitude? Interestingly, voltage magnitude is not dependent upon one generator input property, but rather 2. First, voltage magnitude is directly proportional to DC field current, which kind of makes sense. More DC field current results in a stronger rotor electromagnet, thus more voltage induced on the stator coils. Second, voltage magnitude is also dependent upon rotational speed, which again kind of makes sense, given the process of induction, which states a voltage will be induced across the terminals of a conductive coil proportional to the rate of change of magnetism and the number of coils in the changing magnetic field. Note the dramatic emphasis on the phrase rate of change. The faster the external prime mover turns the rotor, the more voltage will be induced across the stator windings. This is to suggest that not only is voltage magnitude dependent upon 2 input properties, but also rotational speed of the prime mover influences not 1, but 2 resultant electrical output properties, frequency and voltage magnitude. This can present a challenge when establishing electrical output with the desired phase sequence, phase shift, frequency, and magnitude. Follow this example. Consider a rotor spinning at a certain speed in a given rotational direction inside a stator with a specified arrangement of coils with a certain level of field current. The resultant 3-phase AC electrical output will have a specified phase sequence, phase shift, frequency, and voltage magnitude. If we kept everything the same, i.e. the same rotational direction, inside the same stator, with the same field excitation current, however, stepped up the rotational speed, not only would frequency increase, but also voltage magnitude. Again, if we kept everything the same, i.e. the same rotational direction inside the same stator with the same field excitation current, however step down the rotational speed, not only would frequency decrease, but also voltage magnitude. This presents us with a challenge. Let's say you had a phase sequence, phase shift and voltage magnitude right, but your frequency was too slow. If you stepped up rotational speed to the proper frequency, you'd also increase voltage magnitude, potentially overshooting your desired specification. This begs the question, how the hell do you set up a generator such that it delivers a desired phase sequence, phase shift, frequency, and magnitude if one input, rotational speed, influences two properties, frequency and voltage magnitude? The answer is, establish desired phase shift, phase sequence, and frequency first, and don't worry about voltage magnitude until the very last step. Oftentimes, a generating facility will first install a stator with a desired number and physical offset between stator windings to ensure proper phase shift. Next, they get a prime mover rotating in a particular direction to establish a desired phase sequence. Then they ramp up prime mover speed until frequency stabilizes at the desired specification, and then, only as a final step, ramp up field current excitation until voltage magnitude reaches the chosen value. Establishing a phase shift, phase sequence, and frequency first thereby allows an operator to vary field excitation current and field excitation current only to achieve the desired voltage magnitude specification. If you went about this in any other sequence, you find yourself fumbling to achieve voltage magnitude at the expense of frequency, and vice versa. Alright, now that we've got the theory out of the way, let's do a quick practical demonstration and call it a day. For demonstration purposes, I'm going to make use of a 2-pole pair per phase, 200-watt synchronous machine with Y-configured windings designed to operate using a light industrial 120-volt line to neutral, 208-volt line to line, 60 Hz 3-phase AC. In this scenario, the stator is isolated and unloaded, meaning the stator windings are de-energized and not supplying current to any electrical load. All we have is an external DC power supply and some external prime mover. The prime mover can be moving wind, falling water, expanding steam, or an internal combustion engine, but in this lab setting, I'm using a computer-controlled drive dynamometer. The idea is to start turning the rotor with the prime mover with varying amounts of DC excitation to the field and observe the resultant output on the stator windings. Ideally, we should be able to confirm several properties. 1. Prime mover rotational direction influences phase sequence. 2. Field current magnitude influences voltage magnitude. And lastly, 3. Prime mover rotational speed influences both induced voltage frequency and magnitude. An oscilloscope set up to simultaneously display the 3 line to neutral output voltages. V1 in black, V2 in red, and V3 in blue shows no output voltage when the rotor is at rest and field excitation current is at 0 amps DC. One might expect that. The prime mover isn't turning the rotor, nor is there an electromagnet on the rotor. Let's put this thing to work. When an external prime mover starts turning the rotor at 1,500 RPM and no field excitation current, we observe something that might at first seem unexpected. You gotta look close, but the stator windings are experiencing a tiny amount of AC voltage on the order of 2.4 volts RMS, even though there is no electromagnet on the rotor. Why is this happening? The answer is something known as residual magnetism, which is a tendency for ferromagnetic materials, i.e. iron, to retain a little bit of magnetism after a magnetic field has been applied and then removed. You may have observed this phenomenon in your everyday experience with a magnetic screwdriver briefly magnetizing the screw only for that screw to remain magnetic, at least temporarily, after the magnetic bit is removed. That's what's happened to the rotor. Somebody must have excited this rotor some time ago, and a tiny amount of residual magnetism remains. Before we excite this rotor and move on to the rest of this demonstration, I do want to discuss how we can put this residual magnetism phenomenon to use. For the purposes of this lecture series, I've discussed the exciter as if it was a separate external DC source like a battery or some adjustable DC power supply, which it often is. Other types of exciters exist. For example, you could use an external prime mover to start turning an unexcited rotor, exhibiting a small amount of residual magnetism such that a small AC voltage appears in the stator windings, like we're observing right now. That small AC voltage on the stator could then be stepped up using a transformer, and then fed to a power electronics device known as a rectifier that changes AC to DC. This DC electricity could then be fed back to the rotor to create a more powerful electromagnet on the rotor, such that more AC voltage appears in the stator, and this increased AC output is again transformed, rectified, and fed back to the rotor, which creates a more powerful electromagnet, which creates more AC voltage on the stator, and on and on and on in a positive reinforcement fashion. For obvious reasons, this is known as self-excitation. Essential to self-excited generators is that tiny seed of residual magnetism that essentially jumpstarts the whole process. The obvious problem with self-excitation is, what happens if there is no residual magnetism to begin with? As you're no doubt aware, residual magnetism is temporary in nature and fades not only with time, but also heat and impact. The longer you wait, the hotter it gets, and the more you shake it, the weaker the residual magnetism gets to a point it essentially disappears. This wouldn't be an ideal scenario for some mission-critical generator. For this reason, there often exists an external battery backup that can be used to briefly excite the rotor at the start, and then when sufficient electromagnetism on the rotor exists, the self-excitation process can take over. This is sometimes referred to as flashing the field, i.e. jump-starting a self-excited generator with an external DC source. We'll examine self-excited generators and the power electronics devices like rectifiers that make them possible in greater detail in later lectures. Returning to the topic of this lecture, electrically excited synchronous generators, let's keep the prime mover turning at 1,500 RPM and crank up the DC field current to 100 milliamperes. The induced voltage magnitude jumps to 22.7 volts and appears to have a frequency of 50 Hz. We increased field current, and voltage only went up. When we keep the prime mover turning at 1,500 RPM and crank up the DC field excitation current to 160 milliamperes, the induced voltage magnitude again jumps up, this time to 37.4 volts, and frequency remains at 50 Hz. Again, we increased field current, and again voltage went up. Thus far, induced voltage magnitude does indeed seem to increase as we increase field current. Now let's keep the DC field excitation current at 160 milliamperes and increase the prime mover speed to 1800 RPM. Something interesting happens. Not only does frequency increase to 60 Hz, but also induced voltage magnitude jumps to 45 volts. Interesting indeed. Prime mover rotational speed appears to influence both induced voltage magnitude and frequency. Thus far, the prime mover has been turning this rotor in the clockwise direction. For all these samples, we've observed a sequence of V1, V2, V3 with a relative phase shift of 120 degrees between phases. Let's try this in reverse. When we start spinning the prime mover at negative 1800 RPM, or 1800 RPM counterclockwise, and keep field current at the previous level of 160 milliamperes, we still observe 45 volt output at 60 Hz. However, phase sequence is flip-flopped. Note the oscilloscope tray shows a reverse sequence of V1, V3, V2, still with a relative phase shift of 120 degrees between phases. This demonstrates prime mover rotational direction influences phase sequence. In this short demonstration, we've confirmed several important properties. Notably, prime mover rotational direction influences phase sequence, field current magnitude influences induced voltage magnitude, and lastly, prime mover rotational speed influences both induced voltage frequency and magnitude. In ordinary circumstances, we call it a day, but I just cannot resist in messing with this setup a little bit more. Let's say we're trying to establish light industrial, 120 volts line to neutral, 208 volt line to line, 60 Hz 3-phase AC with a 1-2-3 phase sequence. We're almost there. Let's take it all the way. Let's return prime mover rotational direction back to clockwise so we get our desired 1-2-3 phase sequence. Let's keep it rotating at 1800 RPM since this was giving us our desired 60 Hz output. At 160 milliampere field current, we again observe 45 volts. This is well shy of our 120 volt line to neutral goal. What to do? We got two options: increase field current or increase the speed. What would you do? If you said increase speed, you are wrong. Yes, increasing speed would increase voltage magnitude, however, it would also increase frequency. We're already at the desired 60 Hz, so it's in our best interest to keep speed at 1800 RPM and just vary field current since it influences voltage magnitude only. At an increased 210 milliamperes of field current, voltage magnitude rises to 57 volts and frequency remains 60 Hz. When I step field current up to 350 milliamperes, voltage magnitude rises to 85 volts and frequency remains 60 Hz. At 410 milliamperes of field current, voltage magnitude rises to 98 volts and frequency remains 60 Hz. When I step up field current to 585 milliamperes, voltage magnitude rises to 116 volts, and frequency remains 60 Hz. So close. Just a little more field current. Way too much. At 720 milliamperes of field current, voltage magnitude rises to 127 volts and frequency remains 60 Hz. We've overshot our desired voltage magnitude. Let's dial field current back a bit. At a reduced 634 milliamperes of field current, voltage magnitude drops back to our desired 120 volts and frequency remains 60 Hz. Phase sequence, phase shift, frequency, and voltage magnitude are exactly what we want. Perfect. Am I right? Not really. Keep in mind, for the purposes of this demonstration, this generator is isolated and not supplying any electrical load. It's just sitting there looking pretty, but really not doing any work. If you think about it, this generator is not only not connected to some larger grid, it's not even connected to any loads in any isolated grid. An analogy might be installing and setting up the first generator on some small island community with no other generators. Before you start supplying electricity to any of the grass huts, coconut farms, and fish processing facilities on this island, it's probably a good idea to establish a desired phase sequence, phase shift, frequency, and magnitude before doing so. We'll examine in an upcoming lecture how actually connecting to an electrical load and how varying the magnitude and nature of that electrical load can influence the generator's output and how an operator can compensate for these changing demands. Until then, this concludes this lecture. In conclusion, we examined electrically excited synchronous generators in the unloaded condition. We learned that the physical construction of the prime mover influences phase shift, rotational direction of the prime mover influences phase sequence, field current strength influences voltage magnitude, and prime mover rotational speed influences both frequency and voltage magnitude. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.